Yo, 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 yo. Let's see, does this sound good? Okay, nice. Let's do some more Scheme. I want to do some Scheme. If you don't know from last time, I'm following this book called, let me search it up. Structure and Interpretation of Computer Programs. So this book, it's a real like academia type book. Usually I don't read that much, I'll admit, but here it is. Let me get a better picture. So this is the book that I'm reading. I'm following through it. So that's what these streams are going to be about. I'm on Christmas break right now, and I want to get through this book as much as I can. Most realistically, it's a long book. I probably won't, because I'm not interested in rushing this process. If I was interested in rushing it, I probably could, but I want to do all the examples, all the exercises. I want to read it closely. I want to understand it, have a good comprehension of this book, because I really do like this book. It's extremely difficult though, for me at least. So we'll see how it goes. So let's go ahead and get started. There's also these lectures online, MIT OpenCourseWare. They're super, super old. This is so wrong. This is not from 2005. This is from 1986. So it's super old. It's honestly crazy watching it. Yeah, VHS tapes. Well, let me actually switch it over to the scene. My bad. Thought you could see it. So yeah, this is the old lectures that I'm following too, as like a little side thing. I'm mostly going through the book though. The lectures are just to clarify some things, because the book is kind of a sink or swim book where it really just like forces you to figure stuff out. It doesn't really handhold at all. But I found this website that's great gives you the solutions to all the exercises in the book, which is honestly super good. But let's get started. So, and I'm just gonna put this reading symbol here whenever I'm actually reading on the stream, because that way you know like what I'm talking about, because I like to read out loud. I don't know why. Let me see something actually. Why does reading out loud help me better understand? I don't want to read it. Sharpens your focus and eliminates distraction. Yeah, I don't know if you guys have this too, but like reading out loud, it really makes me understand it better, because it makes me feel like I'm teaching. And if I feel like I'm teaching something, I feel like I try harder to understand what I'm trying to say. When I read silently, it feels like a very passive activity, to where I'm like doing something that just goes right over my head. So let's open this up. So last time I was doing, so we're still in chapter 1. I'm still thinking, because I have a GitHub repository, I'm still deciding how I want to go about this stuff. I'm thinking I'll separate them into subsections, and then I'll post it on the GitHub. But I don't know, because each of the chapters is extremely long. But I'm thinking I'll go like 1.1, 1.2, 1.3, stuff like that. in my organization. So yeah, honestly, let's just do that. Actually, no, I don't want to. Nah. Too many subfolders and all that. I don't want to deal with that. Let's make this a little bit more casual. Okay. So, I'm on section 1.2, procedures and the processes they generate. So a procedure, by the way, this stream has a lot to do with me trying to comprehend this stuff. Not necessarily like, it's not always going to be the most intriguing stuff right away. Let me open. Let me just open something. So I use Dr. Racket. It's a scheme interpreter. It's the most modern, easy to use one I could find. It's honestly so nice because it's super easy to use and for such a arcane language. So here we go. I got my scheme interpreter going. Okay. So Dr. Racket's nice because it can do a lot of stuff that I want. So we've now considered the elements of programming. We've used primitive arithmetic operations. Shit. We've used primitive arithmetic operations like multiply, add, subtract, divide. We've combined these operations and we have abstracted these composite operations by defining them as compound procedures. Yeah, we've abstracted them by defining them as like either procedures or variables, values. And we've defined them as compound procedures by basically a compound procedure is if you, let's say you had an add procedure, so you wanted to add two numbers. A compound procedure would be, okay, you would take you would call a procedure within a procedure. So let's say you want to add 4 divided by 2 plus 2. Since you have this here and this here, it's compound. Let me actually zoom in a little bit so it's easier to see. Yeah, right there, it's compound procedure. So if you were to run this, it would run 4 divided by 2, which is 2, plus 2 is equal to 4. And I think there is a square root procedure built in. So if I wanted to take the square root of 4.0, it should give me 2.0. Yeah. So I did a lot of this earlier in the book. It's like they make a huge deal out of it for some reason, but it's built into the language scheme. I think they just wanted to show you how Newton's method of approximation works and how like the whole black box, like how to build a bunch of small procedures to combine them to create a big procedure. I might not be the best at explaining it, but that's the whole point. So, if that is not enough to enable us to say that we know how to program. Oh shoot, okay. Our situation is analogous. See, they use high language like this where I'm just like, what the hell does that mean? I know it means comparable, yeah. Like similar to. Analogous, like related to, similar. So, our situation is analogous to that of someone who has learned the rules for how the pieces move in chess, but knows nothing of typical openings, tactics, and strategy. So yeah, so basically they're saying, I know the different fundamental aspects of, say, scheme or programming. Like, I know about procedures and data, and I know how to put them together somewhat, but I don't necessarily know all the strategies and tactics to be able to control the flow of data at a large scale. Like the novice chess player, we don't yet know the common patterns of usage in the domain. So yeah, I don't yet know the common practices, I guess you could say. We lack the knowledge of which moves are worth making. You know what? I'm gonna add something to it. Let's see. I think this could be better if I do this right. So let's say I'll be like, okay. I'll say what chapter I'm on. I'm on chapter 1.2. It's kind of cool. And then I think I'll take a picture of the book. This will be the picture. I'll just put it in downloads real quick. Just put an image, book, image. As you can tell, my organization is weird. Apply alpha in linear space. Upload image when not showing. Unload image when not showing. Sure. No, I don't want to unload it. Yes, I do. So... that looks trash. That looks so bad. It's not even funny. SICP. It's not transparent. That's cool. I like that. Okay, it might look weird, or it might be fine. Let me check how this looks on my end. Let's see how this looks. Let me go on YouTube, honestly. Okay, that looks awesome. Okay, back to it. So, we lack the knowledge of which moves are worth taking, which procedures are worth defining. We lack the experience to predict the consequences of making a move. So yeah, if I made a certain procedure and I did it in a certain fashion, certain way, how would it mess me up? Would it cause the system to scale in a super efficient, dangerous way? Well, you need to have common practices to be able to figure out, okay, what's the best way to do things? So sorry, I have notes on the side that I write on. I know you can't see, but which procedures... So basically, a common practice is which procedures are worth defining. Basically, when do you need a whole new procedure to do something? Or when do you just throw that code into an existing procedure and just call it a day? And how to predict the consequences of executing a procedure. So it is kind of like chess. That is a weird way to look at it, but okay. So it's kind of like chess. Do I like this green? No, I do not like that green. Green looks kind of weird. I feel like orange sometimes looks really cool for some reason. Or even like, yeah, that looks kind of weird though. I think I need a different font. I actually like that. It's cool. And then change the color, pink? I don't know about pink. This looks like a cool color, yeah. Yeah, I kind of like that. Okay, there you go. You should be able to see it. So, yeah. So basically this book is calling me a noob. It's calling me someone who lacks the experience. Which is honestly messed up. Okay. The ability to visualize the consequences of the actions under consideration is crucial to becoming an expert programmer. So, the ability to visualize the consequences of the actions under consideration is crucial to becoming an expert programmer. So, okay, so as a master programmer, yeah, because if you're contributing to a large system, you know that whatever you put in there has the power to destroy that system or wreak havoc on it. So you need to, as a master programmer, you must be able to visualize the consequences of the actions under consideration. Okay. But just as it is in any synthetic creative activity, in becoming an expert photographer, for example, one must learn how to look at a scene and know how dark each region will appear on a print for each possible choice of exposure and development conditions. Only then can one reason backward, planning, framing, lighting, exposure, and development to obtain the desired effects. So it is with programming, where we are planning the course of action to be taken by a process and where we control the process by means of a program. So we plan the course of action to be taken by a process, and then we also know how to control the process by means of a program. So the program controls the flow of the processes. So basically what this all means is that you need to know how to wield the power that is being able to define and make any kind of procedure that you want. And it's a lot of freedom, and that's what makes it hard. But if you're able to control that freedom, then you can really create some powerful chains of procedures to create programs, large programs. And that's a good way to look at it. And I guess, like, what I'm thinking is that only then, so yeah, like, programming seems like a lot of organizational skills need to be used. So to become experts, we must learn to visualize the processes generated by various types of procedures. Yeah. Only after we have developed such a skill can we learn to reliably construct programs that exhibit the desired behavior. So if you have that intuition, I guess you could say, then you could start building large-scale programs that do what you want. It doesn't even have to be large scale. It can be like just any non-small scale. A procedure is a pattern for the local evolution of a computational process. It specifies how local evolution. It specifies how each stage of the process is built upon the previous stage. How each stage of the process is built upon the previous stage. Okay. We would like to be able to make statements about the overall or global behavior of a process. whose local evolution has been specified by a procedure. Let me read that again. We would like to be able to make statements about the overall, basically global behavior of a process whose local evolution has been specified by a procedure. Yeah, so basically the global behavior is determined by a chain of local processes, basically. Processes that have local scope within them, so you can abstract it. You can just use a bunch of those to create some kind of global behavior or process. This is very difficult to do in general, but we can at least try to describe some typical patterns of process evolution. Yeah, that's the problem I have, is that like every time I try to make a program, I know the parts very well. Like I know what a while loop does, I know what a for loop does, I know what conditionals do, I know what variables and functions or procedures do in classes. And I know all those. I know all the pieces, and I know how to put them together. But once it gets, beyond a very small scale, that's when it all falls apart and I don't know how to scale it. And then it becomes a daunting task where it's like overwhelming. So I need to be able to have the intuition to put these things together at scale. So embedded definitions must come first in a procedure body. The management is not responsible for the consequences of running programs that intertwine definition and use. So where's that from? Oh, that's talking about when you're defining a procedure within a procedure. You have to have those auxiliary procedures come first in the procedure body. If you have them come like after or whatever, it's not gonna just like magically know. You have to have it in a specific order, basically. So, okay, figure 3. A linear recursive process of computing factorial 6. So what does factorial mean? Factorial meaning math. You know what? Let me use ChatGPT. I don't like Google. Create a new one. Factorial meaning math. So in math, the factorial of a non-negative number n. So this next section deals with, this next figure deals with factorials. In this section, we'll examine some common shapes. Shapes are tactics, I guess you could say, for processes generated by simple procedures. We'll also investigate the rates at which these processes consume the important computational resources of time and space. The procedures we will consider are very simple. Their role is like that played by test patterns in photography, as oversimplified prototypical patterns rather than practical examples in their own right. So yeah, the rates at which these processes consume the important computational resources of time and space. So a factorial is basically, what is a factorial? So it's kind of like summation, but it's the product all positive integers. From 1 to n. So let's look at the formula. So n factorial is equal to, it would be well, multiplication is commutative, so it's fine. It should be n times n minus 1 times n minus 2 times dot 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 times times 1 eventually, because it'll go down to 1. So an example of 5 factorial would be equal to 5 times 4 times 3 times 2 times 1. That's equal to 20, 60, 120. And then the factorial of 0 is equal to just 1. Factorials are used in permutations, combinations, and other areas of math. Let me see, so they are multiplication, not exactly that's what I literally said though, like I said it's multiplication form of summation, and then it says no. Okay. So I'm looking at this example. So factorial 6, factorial 5, factorial 4. This is a linear recursive process for computing 6. So let's look at this. 1.2.1. So we begin by considering the factorial function defined by, so I got that down. There are many ways to compute factorials. One way is to make a use of the observation that n factorial is equal to n times n minus 1 factorial for any positive integer n. Wait, so it's equal to, n factorial is equal to n times which is equal to n times n minus 1 factorial. Okay, I see. Yeah, that makes sense. Thus we can compute n factorial by computing n minus 1 factorial and multiplying the result by n. If we add this stipulation that 1 factorial is equal to 1, this observation translates directly into a procedure. Yeah, we have to have some kind of conditional saying. Because 1 factorial is 1. So now we can create a procedure. So let's get to coding. So the procedure would be, let's define it, factorial, taking an n, and then what will we do? We'll say, okay, so basically it ends up being n times n minus 1. But first we got to check if n is equal to 1. If n is equal to 1, then what will we do? Well, we'll return 1. And then alternatively, we would have to call some kind of function. So it would basically do factorial operation, which is basically, this is the multiplication of n times n minus 1, the factorial of n minus 1. We'll call this factorial. One, two, three, four, 5. I only have 1, 2, 3, 4, 5. Yeah, so I got it right. So then, but this factorial function, so basically it would do a recursive call, and then it would go, okay, it'd go back and then be like, well, whatever n is, factorial of, so n would stay the same. Let's say n is 2, it'd be 2 times, the factorial of 2 minus 1, 2 times 1, that produces 2. So 24. So yeah, this works. So it's a really simple but nice. It's kind of elegant linear recursion. So factorial 5 should be 120. There we go. So 5.0. Okay, I'm back. So, yeah, so that works. We can use the substitution model of section 1.1.5 to watch this procedure in action computing 6 factorial as shown in figure 1.3. So it goes factorial 6 calls in 6 times factorial 5, 6 times 5 times factorial 4, 6 times 5 times 4 times factorial 3, and then it just keeps going until it gets 1. So it kind of creates that shape where it goes so that linear recursion. So that linear recursion. Now let's take a different perspective on computing factorials. So that linear recursive process is pretty interesting. So it's like you start out with factorial 6, and then that factorial 6 leads to 6 times factorial 5, and then that leads to 6 times 5 times factorial 4. So it's like it goes down, and then that leads to that leads to 6 times 5 times 4 times factorial 3. And so it keeps going. So yeah. So it goes. Wow, and it just keeps going. So it goes, does that, and then it goes 6 times 5 times 4 times 3 times. Times factorial 2. So 1, 2, 3, 4, 5. And then it leads. And then it keeps going, so it keeps going down, and then it points back out. So it's kind of like a triangle in a way, or like some kind of pyramid that's shifted. It's rotated 90 degrees. So yeah, now let's take a different perspective on computing factorials. We could describe a rule for computing n factorial by specifying that we first multiply 1 by 2, then multiply the result by 3, then by 4, and so on until we reach n. More formally, we maintain a running product running with the counter that counts up from 1 up to n. We can describe the computation by saying that the counter and the product simultaneously change from one step to the next according to the rule. So we can describe computation by saying that the counter and the product simultaneously change from one step to the next according to the rule. So the counter times the product is what the product is every new rule, and then the counter is just a simple iteration. It's just a simple counter plus 1. So in stipulating that n factorial is the value of the product when the counter exceeds n. Once again, we can recast our description as a procedure for computing factorials. In a real program, we would probably use the block structure introduced in the last section to hide the definition of factor. Yeah. Yeah, so let's look at the code. So a different way to do it would be to say that the product is, so every step the product is equal to the counter times the product, and that every step the counter is equal to the counter plus 1. Simple plus 1. So let's define a factorial. N be our argument, bounded argument. And then what you do basically is what we do is initially say so we'd create we avoided doing this here so as to minimize the number of things to think about at once. So we have this, which basically does, what does it do? Okay, so what this does is basically so where did my pencil go? I don't even know where that went. Okay. So for each factorial, we're basically saying, okay, is the value of the product, so if basically, I think we'd say if the counter exceeds, no, I think we'd do that in the factorator. The value of the product when the counter exceeds n. So I think in here we would just call the iter function procedure. Honestly, I kind of just want it to be in here. Iter. Takes in a product and a counter. And then we say, okay, if the counter is greater than n, so if the counter exceeds n, then what do? We return the product. Else, we call the iter again, and we pass in the new product, which is the product times the counter. It's the counter. And the counter plus 1. Yeah. And then we would just call this. So we'd do the iter. The product would initially be equal to... what would the product initially be equal to? Say probably 1. And then the counter would initially be equal to... 1 as well. Yeah. If we called this factorial 5 again, it should be 120. Yeah, nice. So it works. So basically what this does is it has 2 procedures. It has one in a block structure. So it has an auxiliary procedure that iterates. So if you want the factorial of some number n, goes in, calls another, so it has another companion procedure or auxiliary procedure that checks, okay, is the counter greater than n? If it is, return the value of the product. If it isn't, then you recurse this iter function procedure and you pass in a new product, which is the product times the counter, and a new counter, which is the counter plus 1. And then we actually call this. And we start at 1 for both of these. We start at 1 on the product, we start at 1 on the counter, and it'll equal 5. Because if we started out at 2, I think this would be equal to... Okay, it would stay equal to what? We start out on 5. 4. Because what is that? It's the counter. If you start out at 1, if I started out at 0, it would do 1 extra, basically. No? It's not, so it does it. Oh, because the counter, yeah, it has to do with it. So if you multiplied by the counter, you'd be multiplying by 0, so it'd give you 0 straight out. If you multiplied by 2, why does it work with 2? Multiply by 2, product times 2, So the initial product is 1, so it'd be 1 times 2, 2. If it's 1, it's 1 times 1. Okay. Yeah. So yeah, another way to write this would be the version 2 of this would be taking an n, of course, and then what would we do? What would we call the iter function, which takes in something. I don't know what it would take in right now. So should take in a product, counter in an n. So yeah, this would take in some kind of product, counter an n, so it's 1, 1, and an n. And then this would take in, so this would basically do all that logic. So you check, okay, is the counter greater than n? If it is, then return the product. If it isn't, then call this function again, and then pass in, what would we pass in? We'd pass in, same thing basically, product times counter, the counter plus 1, pass in n, of course. So yeah, so let's try this one. Factorial v2. Oh, I didn't. So counter. Yeah, so this works too. There's 2 ways to do it, but this way is a lot better. I like this way, because it sticks with that block structure and it keeps it. That iter function, this is not going to help anything else in a program. This is specifically an auxiliary function for factorial, so let's just keep it within this local scope of this, and that way we also don't have to pass in an n for this either. We can just pass in the product and a counter. Nice. So as before, we can use the substitution model to visualize the process of computing 6 factorial as shown in 1.4. Forgot what the substitution model is again. Let me go back and look. I think it's like where you throw certain things in there. Substitution, it can be taken as a model that determines the meaning of a procedure application insofar that the procedures in this chapter are concerned. So yeah, so if we took it like this, Oh, basically you just keep substituting until it's reduced. Yeah, so that's what that means. So if I look at figure 1.4, take factorial 6, and then basically what you're doing is you're substituting, so running the fact iter, and then you're substituting a 1, a 1, and a 6 in there. And a 1, a 2, a 6, a 2, 3, 6, a 6, 4, 6, a 24, 5, 6, a 120, 6, 6, and then a 720, 7, 6. And then finally, the 7 is greater than the 6. Otherwise, the counter is greater than n. So then you just return that product 720. So, compare the two processes. From one point of view, they seem hardly different at all. Both compute the same mathematical function in the same domain. Each require a number of steps proportional to n to compute n factorial. Indeed, both processes even carry out the same sequence of multiplications, obtaining the same sequence of partial products. On the other hand, when we consider the shapes, yeah, so the substitution model reveals the shape of expansion followed by contraction, indicated by the arrow in figure 1.3. Expansion occurs as the process builds up a chain of deferred operations. In the case of chain of multiplications, the contraction occurs as the operations are actually performed. So this type of process, characterized by a chain of deferred operations, is called a recursive process. Okay, nice. So, recursive process. So it's a chain of deferred operations. What does deferred mean? Like, I know what it means. Like, I think it's to hand off to something. Oh yeah, so basically like do it, keep, carries over. So a chain of deferred operations is a recursive process. So carrying out this process requires that the interpreter keeps track of the operations to be performed later on. It requires that the interpreter keep track of the operations to be performed later on. Okay. The computation of n factorial, the length of the chain of deferred multiplications, and hence the amount of information needed to keep track of it, grows linear with n. It's proportional to n, just like the number of steps. Such a process is called a linear recursive process. So, in the computation of n factorial, the length of information needed to keep track of it grows linear with n. So basically, however many n's you have, so the value of n is how much it is, directly proportional to the value of n. So it scales with how big n is. By contrast, the second process does not grow and shrink. At each step, all we need to keep track of for any n are the current values of variables product, counter, and max count. Okay. Oh yeah, so that's the first one, and then the second. So that n times factorial n minus 1 is linear. And then the second one counter and max count. We call this an iterative process. Are the current values of the variables product, counter, and max count. In general, an iterative process is one whose state can be summarized by a fixed number of state variables, together with a fixed rule that describes how the state variables should be updated as the process moves from state to state, and an optional n test that specifies conditions under which the process should terminate. In computing n factorial, the number of steps required grows linearly with n. Such a process is called linear iterative. Okay. So in general, an iterative process. Okay, let's look at the iterative process. Is one whose state can be summarized I think it would be like a loop, basically. Yeah, let me look at this. So, iterative process. Yeah, I think it's a loop. Whose state can be summarized by a fixed number of state variables These state variables determine the state of the loop. Together with a fixed rule. That describes how the state variables should be updated. That describes. Okay, yeah. Describes how they should be updated. Basically, like, the count should be updated every iteration of it. As the process moves from state to state, and an optional end test. An optional end test that specifies conditions under which the process should terminate. Computing n factorial, the number of steps it requires, grows linearly with n. Such a process is called a linear iterative process. Yeah, so if n is a really big number, it requires a lot more iterations than if it was like a tiny number. Awesome. So the contrast between the two processes can be seen in another way. In an iterative case, the program variables provide a complete description of the state of the process at any point. Contrast between the two in an iterative case, the program variables provide a complete description of the state of the process at any point. Program variables provide a complete description of the state. Yeah. In an iterative case, the program variables provide a complete description of the state of the process at any point. Yeah, so they show like what the state is. If we stop the computation between steps, all we would need to do to resume the computation is to supply the interpreter with the values of the three program variables. If we stop the computation between steps, all we would need to do to resume the computation is to supply the interpreter with the values of the three program variables. Yeah, not so with the recursive process. In this case, there is some additional hidden information maintained by the interpreter and not contained in the program variables, which indicates where the process is. So yeah. So yeah, recursion maintains some hidden information. Info which indicates where the process is currently. Where the process is. In negotiating the chain of deferred operations. The longer the chain, the more information must be maintained. So yeah. More info must be maintained. So when we discuss the implementation of procedures on register machines in Chapter 5, we'll see that an iterative process can be realized in hardware as a machine that has a fixed set of registers and no auxiliary memory. In contrast, realizing a recursive process requires a machine that uses iterative process can be realized in hardware that has a fixed set of registers but doesn't have any auxiliary memory. contrast, realizing a recursive process requires a machine that uses an auxiliary data structure known as a stack. Yeah. So recursion requires a stack. So recursion requires a stack. So in contrasting iteration and recursion, we must be careful not to confuse the notion of recursive process with the notion of a recursive procedure. Okay. So when we describe a procedure as recursive, we're referring to the syntactic fact that procedure definition refers to the procedure itself. Yeah, so basically in a recursive procedure, that procedure's body contains itself somewhere. Yeah. And then a recursive process but when we describe a process as following a pattern that is, say, linearly recursive, we are speaking about how the process evolves, not about the syntax of how a procedure is written. Speaking about the fact of how the process evolves, not about the syntax of how the procedure is written. It may seem disturbing that we refer to a recursive procedure such as fact iter as generating an iterative process. However, the process really is iterative. And yeah, that is an iterative function. Oh, but it does call to itself. It may seem disturbing that we refer to a recursive procedure such as fact iter as generating an iterative process. Because it does call to itself. That's what's kind of weird. However, the process really is iterative. Its state is captured completely by its 3 state variables. And the interpreter needs to keep track of only those 3 variables in order to execute the process. Really? So, if you looked at that, one, two, three. So the counter cube start with state, product, max count. Yeah, it does, because the whole thing is basically saying, okay, well, if the counter is greater than the max count, basically a state is in a certain way, then you return this. So that actually makes sense. Even though it does involve recursion in itself, it's overall an iterative process because the process is controlled by those state variables. One reason that the distinction between process and procedure may be confusing is that most implementations of common languages are designed in such a way that the interpretation of any recursive procedure consumes an amount of memory that grows with the number of procedure calls. So Ada, Pascal, and C are designed in such a way that the interpretation of any recursive procedure consumes an amount of memory that grows with the number of procedure calls, even when the process described is, in principle, iterative. The interpretation of any recursive procedure consumes an amount of memory that grows with the number of procedure calls. So how many times do you call that procedure in the recursion? That's how much memory you're going to use. It grows, scales with that. Even when the process described is, in principle, iterative. As a consequence, these languages can describe iterative processes only by resorting to special purpose looping constructs such as do, repeat, until, for, and while. So these are loops. So basically, like in C and most, I'll just say, common programming languages, iterative processes are used by special purpose looping constructs. So it is hard to blend one recursion and iteration in a procedure. Scheme differs from this. Okay. So the implementation of scheme we shall consider in chapter 5 does not share this defect. It will execute an iterative process in constant space, even if the iterative process is described by a recursive procedure. Yeah. So basically you can call an iterative process in a recursive function or recursive procedure. You can do both. So they kind of blend. An implementation with this property is called tail recursive. With a tail recursive implementation, can be expressed using the ordinary procedure call mechanism, so that special iteration constructs are useful only as syntactic sugar. Wait. So with a tail recursion implementation, iteration can be expressed using the ordinary procedure call mechanism, so that special iteration constructs are useful only as syntactic sugar. Okay. That means that tail recursion, recursive iteration, can be expressed using ordinary procedure call mechanisms, so that special iteration constructs are useful only as syntactic sugar, basically like a different way to do the exact same thing. Stylistic choice, kinda. Tail recursion has long been known as a compiler optimization trick. A coherent semantic basis for tail recursion was provided by Carl Hewitt in 1977, who explained it in terms of the message passing model of computation that we shall describe in Chapter 3. Inspired by this, Gerald J. Sussman and Guy Lewis Steele Jr. constructed a tail recursive interpreter for Scheme. Steele later showed how tail recursion is a consequence of the natural way to compile procedure calls. The IEEE standard for Scheme requires the Scheme implementations be tail recursive. So tail recursion can be expressed using the ordinary procedure call mechanisms, so that special iteration constructs are useful only as syntactic sugar. I'll say long been known as a compiler optimization trick. Cool. So now I'm on exercise 1.9, then I'll do 1.10. So 1.9, each of the following two procedures defines a method for adding two positive integers in terms of the procedure inc, which increments at arguments by 1, and dec decrement, which decrements in arguments by 1. Using the substitution model, illustrate the process generated by each procedure in evaluating 4 plus 5. Are these processes iterative or recursive? Okay, so yeah, so basically we would take, okay, you have a process plus, which takes in A and a B. And they say if A is equal to 0, then return B. If not, then evaluating 4 plus 5. Okay. So it'd start like this. It'd be call an increment, which increments its argument by 1 index. Okay. So if not, you want to increment all of it. But you're calling that plus. You basically, so you'd increment that. A plus B, so if A is equal to 0, I'd say they're iterative. Because state is controlled by variables. Yeah, state is controlled by the variables. But I gotta illustrate these processes, so let's at least do the bottom one first, because that one looks easier to do. So you got plus, and then you're gonna throw in a 4 and a 5, and then what I'm gonna do after that is, so A is not equal to 0, of course. So you're gonna call it again. Then you're going to decrease A by 1. So it's going to be 3. Then you're going to increase B by 1, so it's going to be 6. One 8. So equals 9. So yeah, I would consider this, it actually could be recursive in a way, but no, it's controlled by that variable. So I would say definitely it's an iterative process. an iterative process. And then for the top one, you'd have it, okay, so you'd be like, start by throwing in the 4 and the 5 to this function, this plus function, and then you go in, check if it's, so it's not equal to 0, of course. So you'd call it again, but what you do is, it's so weird because you're increasing the outside of the function, so it increments the argument, so it would increment both of them, I guess. But what it's doing though is so you're incrementing the recursion of the function. So you're going to call that function again. What you're going to do is you're going to decrease a, so you're going to decrease it to 3, and then you're going to pass in 5. So that's going to, and then it's going to increment that. Which is kind of crazy because when it increments that, that means it will basically result in problem is I don't think that'll ever go anywhere. So let me actually write that. So first you say, okay, is a equal to 0? If it is, return b. If it's not, then we're gonna increment so increment increases so increment, just want to increment x, which basically takes x and adds 1 to it. And then we're going to decrement x, basically takes x and subtracts 1. Okay, so we got our increment and decrement. So yeah, so in that case, what you would do here is, well, let's run the function first of all. For c plus. So what did I do wrong? I'm gonna call it plus. Oh shit. I actually fixed it. Let's call it, I have a feeling that plus is probably defined already. Okay, so it does work. It does work, yeah. Let's just call it plus. I just don't get how this works, because how do you increment a whole ass function? I guess what you'd be doing is you'd be like, okay, so when you're incrementing a function, basically you're saying, okay, I'm going to increment, but I'm going to call this function. And you're going to keep incrementing past it, so but that's so strange. So you okay, so what are you doing? When you increment, should you place that plus, you would throw in, you'd be incrementing the result of throwing in the decrease in A, which would be decrease A would make it 3 and then keep B the same. And you'd increment that, but I think you would keep going. Maybe you would increment both of them, but I didn't think you could do that. Maybe you would keep trying to do it until you get to 0. Yeah, so I think what you would do is, once it's that, then it returns B, but you've done this 4 times, so it's +1, basically. +1, +1, +1, so that results in 1, 2, 3, 4. So then you would end up with 5, which is B plus 4 increments is equal to 9. So that works. And that increment is kind of keeping track of things. I think it's an iterative process as well. Yeah, I think it's an iterative process. I'm gonna take it as that. Let's see if I got it. What? Oh, because of it's expanding and contracting. Yeah, this is iterative. But how is this... Okay, so how is this a recursive process? Because... So, okay, of course, at first you take in 4 and a 5. And then after that, what are you doing? Well, you're replacing, so you're passing in... Yeah, and then you're calling the function. But you're calling it with a 3 and a 5. And what does that do? I guess it calls... So if you call that increment function on that, then you end up going down and you call the increment function on the increment of that. Increment function on the increment of decreasing 2 plus 5, and then you do it again, call in the increment of the increment of the increment of 1 plus 5, And then do it again. Call the increment of the increment of the increment of the increment of 0 plus 5. And then that should return to that should return 0, because once that returns 0, or no, it'll return 5. So how would it do that though? Because it would return the increment of the increment 5, and it'll call that function again, which will get increment of the increment of the increment and the function results in 5. And then if you call that 5 in there, in the increment basically, oh okay, I see. So now that you have that 5, you call the increment of the increment of the increment of 5 increase 1 of increase 5, which would basically be increment of 6. And then that means you have the increment of the increment of the increment 6, which is 7. And then that results in the increment of increment 7, which would be 8. And so increment 8 equals 9. So this is an expansion, and then a contraction. So an expansion and a contraction results in the recursive process. Okay, I understand this a lot better. For deferred operations. Yeah, because it's deferring it for a later date. So you 1, 2, 3, 4. No. 1, 2, 3, 4. So yeah, it has 4 deferred operations. This means that it's pushing it till whenever it contracts, and then once it contracts, it can use those deferred operations which are evaluated. So then it'll increase 5, it'll increase 6, it'll increase 7, it'll increase 8, and then lastly, once it contracts, if you increase 8 1, it'll equal 9, which will get you the thing. Both seem pretty logical, but I feel like the iterative process feels better. Feels faster, I think. Check that one off the list. How long have we been going for? 1 hour 57 minutes. Nice. Let's change the song. Let's do one that's cooler. Yeah, I like this one. Let's see how this is going. I haven't even checked the stream on my end. Let me check this out real quick, guys. Let's see how this is going. I haven't even checked the stream on my end. Let me check this out real quick, guys. That should return. Yo, I'll be right back. Be right back pretty soon. Okay, bet. I'm back. Just had to get some water. Some water and some Pepsi for later. I'm thinking we'll go super long today. I'm on Christmas break. I literally do not care. I just want to learn as much as I can from this book because I really like it. So let's do this. We're on exercise 1.10. Just take a drink of water real quick. Okay. Let's do this. So, exercise 1.10. Exercise 1.10. So 1.10, the following procedure computes a mathematical function called Ackermann's function. So, yeah. What are the values of the following expressions? A1, 10, A2, 4. Okay. So let's check this out. So, yeah, let me do pseudocode. I'm gonna try pseudocode on just like a Notepad++. Call it a day. Kind of like this. Except, let's edit the settings. Let's make it look nice. Consolas is nice. Cambria Math. No. Okay, I kind of like that. So, okay. So if we have this function, and it goes like this, I'm not going to run it because it's cheating for this example, but let's at least type it out. So it's called A for Ackermann's function, and it takes in an x and a y as its argument, runs a condition. So this is the clause. The clause is basically is y equal to 0, and if it is, then you return 0, and then if it isn't, you run another clause. So the second clause basically says, okay, is x equal to 0? If it is, you return 2 times y. And if that isn't true, then we want to see, okay, is y equal to 1? If it is, return 2. And then if none of these are true, we call the function again, recursively, I guess you could say. Call the recursive procedure. Pass in x minus 1, and then you pass in. Whoa, okay. And then you pass in the function recursively as well. Whoa, that is that is interesting. You pass in the function recursive as well. You pass in an x, and then you pass in y minus 1. That's your function. My headphone died real quick, but we chilling now. So let me charge it real quick. Nice. So it's kind of interesting, to be honest. Like, I don't really know how to feel about this, because it's a recursion. So you're calling the function recursively. Basically, it's a recursive. It is a recursive procedure. It's not necessarily a recursive process, but it's a recursive procedure, because what you're doing here is the definition of this procedure calls itself, but it also, when it calls itself, it throws itself into the argument of itself. So that's, I've never seen that. And honestly, it's kind of crazy. So I have a feeling this might be a little challenging. So we got to see what it'll be. We pass in 1 and 10. And then if we pass in 2 and 4. If we pass in 3 and 3. So this, what would happen when we call this function like that? So I'm going to draw the pseudocode here of what basically the substitution model of it. And I'm going to see what the heck happens. So let's see what the values of this expression would be. So for this case, I'm not even sure, because, okay, so let's say you pass in 1 and 10. So A, 1 and 10, okay. Taking the conditional, okay, you say pass in 1 for x, 10 for y. So you say the conditional is y equal to 0. Well, it's not. So you keep going. Is x equal to 0? No, it's not. Is y equal to 1? No, it's not. So then else you do the function again. So you do the function. But the thing that's weird is damn, I love this song. So you're passing in the function. So else you're gonna call the function again. So you're already calling it again. And then, but this time the way you're gonna call it is you're gonna call it with an x minus 1. X minus 1, and then you're going to call it with the function again. You're going to put in x, and then you're going to put in y minus 1. And I think what that will do is that we'll say, okay, well, it'll expand for sure, because it'll go a of I think it'll defer these, that at least, and then it'll call this, which will basically this will basically call itself. It'll call itself again. So it'll call itself, and oh my god, what will that do? I think if it calls itself and it goes down, and what it'll do, will that not just explode in complexity? Because if it goes A and then calls in. This is the function, and the function, and the function. So this function call is calling the function itself. And when that happens is it's. So yeah, it's calling itself right here. Takes in that. Just also gonna call that in too. And it's gonna apply an x. And it's gonna apply a y minus 1. Which is basically 10 minus 1, which is 9. No. X minus 1 is 1. Wait. So I gotta think about this more clearly. I was thinking about the definition. So, calls in a 1 minus 1 for its x, and then one. So, and then a 10 minus a 1. So what that does is I guess it would call that. So what it would do is it would go, okay, that a 1 minus 1 is a 0, a of 0, and then a of a of 1 and but I feel like it would expand in complexity. Yeah, it would have to expand. Because this is a... It's gotta be recursion. Well, let me look at Ackermann's function better. Yeah, it seems like it would explode in complexity. Because what you're doing here is you're going, okay. I think you would keep calling this function until you get something. So you'd say, but would you solve it though? I don't think you would. Because you'd keep going, go A, and then I think you'd go A to the A because you would, because that A is calling an A, so let's see how I did this other one. I'm like so much to keep track of, it's throwing me off. Okay, so I look back at 1.9. So what I did is pass in 4 and 5. 4 is not equal to 0, so it's going to go into the alternatives thing. It'll run itself again, so it'll go, but it'll do that. It's within an increase, so it'll run increase plus 3 and a 5. So you decrease. Okay, I see. So we definitely want to do these, I think. Restart. So pass in a 1 and a 10 for the x and y respectively. And then when you do that, is y equal to 0? No. Is x equal to 0? No. Is y equal to 1? No. So else, do the function again. Call this function, which passes in x minus 1, so 0, and a, which takes in x, which is 1, and takes in y minus 1, which is 9. So then you run that. So a to the 0 is, so that means the x is 0, so you would return you would return 2 times y should be equal to 2 times y, which is a1 and 9. So what is a1 and 9? I guess you'd have to say, okay, there's a1 and 9. Well, a1 and 9 is pass in should have to pass in just basically you'd say, okay, a was x minus 1, 0, and then y is pass in a, x is 1, y is 8. So this would equal 2 times a to the 1 and 8. So you'd keep repeating this process over and over and over. So I'd keep going. Be like, okay, what's a18? Well, a18 is 1. Yeah, it doesn't match any of those cases. So you go into the else case, which you'd call a, and then you'd say x minus 1, so it's 0. And then for y, it's a of 1, and y minus 1 is 7. Okay. So you do that basically. This is equal to, because if you call that, that's equal to calling 2 times a of 1 to 7. 1 and 7. So you'd keep doing this process like over and over and over. This time see, okay, what is A1 of 7? Will be A0 and then A1 of 6. This would be 1 of 6. Say, okay. What is A1 of 6? What's A0 and A1 5? You're like, okay, well, what is A1 5? What's 0 and A1 4? Which is equal to 2 times A1 4. You'd say, okay, what is A1 4? Well, A1 4 is equal to A0 A1 3, which is equal to 2 times A1 3. And say, okay, what is A1 3 equal to? Well, A1 3 is equal to A0 A1 2, which is equal to 2 times A1 2. You'd say, okay, what is A1 2 equal to? Oh my god. They really chose to punish me with this exercise. Jesus Christ. Well, A1 2 is equal to A0 A1 1. Okay, well that's equal to, so the 0 is equal to 0. Get 2 times, so you get 2 times A1 1, which is equal to 2 times 2, which is equal to 4. I'm gonna check it. I feel like I got it right. What is it? 1 and 10? Come on, it's gonna be 4. Oh. Shit. 10, 2, 4, 4. 10, 24. So I got it wrong. But I know this is the first one evaluated. So I think all this would happen and then it would go start evaluating these old ones with these ones. So like for example, what is 2 times A1 9? Well, how is it 1024? I think maybe I didn't write it in the right format because I went A110 is A0, A10, and then I should have expanded this even more. I should have said this is equal to this is equal to times, so times Q times A1 and 9 instead of this. Which is then equal to A 2 times A A0 A18. Well, 2 times what's A1 and 9? So A1 and 9 becomes I don't think you'd have this A. I think you'd have 2 times A0, A18. Which then equals A 2 times A0 and A18. But we actually call it A18. Well, A0, A18. Well, we'd say A18, so A0 times A18, so I feel like I'm right there. I'm right about to get this algorithm or this recursive process. It's definitely expanding because it's expanding quite a bit. I think that should be another A because it's A110. So the 1 and the 10 go. And you're calling an A. Then it's A0. And then A1 and 9, and then this turns into Well, what is A0, A1, and 9? Well, you call that... Shit, wow. So you call that A with the 0, and an A, a 1, and a 9. So when you call that A0 leads to a 2 times Y. But you also have that A19. So you go A 2 times A0 A18. God, man, this is so freaking hard. Oh my god. Wow. They never said it would be easy though. Cheese bag. Wow. I mean, I feel like it's right there on the tip of my tongue, but it's like there's a lot going on. So it's like I gotta be able to think this through. So you pass in the 1 and the 10. And then you look at the conditions and you say, okay, well, I gotta follow the conditions. Well, 10 is not 0, 1 is not 0, 10 is not 1. So we gotta call this function recursive call to it. So we call it, and then we pass in x minus 1. So we pass in a 0, and then we pass in a 1 and a 9. And when we do that, well, we're basically calling the function again. So we call the function, okay, and we're like, okay, x does have a 0, so that returns a 2 times y. So that means the problem is this doesn't make any sense, because this means a 2 times y. But what about the x? Because now we have a 2 times y. Yeah, because it's a 2 times a1 minus y. I don't even think you need that a, because you're not even calling it again. 2 times a minus y, or a1 and 9. So that means you call that, so you go, okay, 2 times a1 and 9, what's a1 and 9? So it'd be 2 times a1 and 9, a1 and 9 is, doesn't follow any of this, so we have to call that a again. So we're going to call an a again. When we call an a, we make the x a 0, and we make the y an a1 8. Yeah, like this. Now that we do that, well, now we need to figure out 2 of them. So we knew that 2 times, so 2 times, we know a0 will result in 2 times y. What is y? Well, it's A, 1, and 8. So that means, I think it'd be 4. And then this would result in, we still need to find A, 1, 8. So what is A, 1, and 8? Well, would it be 1 and 8? It'd be 1 and 7, right? Because if we took in 0, 2 times y, what is y? Well, y is 7, 1 and 7, right? Yeah, 0 and 1 and 8. So then we see, okay, we have multiple times 2's. So A0 goes here, so it's 2 times y. Well, what is y? A1, 8, so it would be A0. Wait, what the fuck am I doing? Holy crap, it's like every time I feel like I'm in a good spot and I feel like I finally understand it, it's like another thing comes at me that I didn't anticipate. Because it doesn't seem like it's expanding in like a typical sense. It feels kind of like it, but not really. Okay. So A0, A19, so A0, so you pass in the 0. Because this subtracts it, so it's 0 and then it's 1 and 9. So that means we're calling it again. Call it again, so A 0, so that means it returns 2 times y. Well, what's 2 times y? It's 2 times this. 2 times A1 of 9. So we do that. 2 times A1 of 9. Well, what's 1 of 9? Pass in a 1 and 9. You have to do this. So that would turn into 2 times A0. Be 2 times A0. And this would turn into A1 and 8. Yeah. So that would turn into 2 times, well, what's A0, A1 of 8? Let's call it. So you put in a 0. Okay, so it turns into a times 2. So 2, so then it times, so 2 times y. Well, what's the y? A1 of 8. Well, what is A1 of 8? You pass in the 1. Doesn't really do anything, so that would turn into, so 2 times A1 of 8 would turn into A0 A 1 and 7. Yeah, like that. Okay. And then what we would do here is, so we have these. Now we gotta find out this, so that A, so it turn into a, you plug in, call it again, so A, the argument 0 and A1 of 7, so 0, x does equal 0, so it's 2 times y, 2 times A1 of 7. Well, what is Well, I think I would do 2 times A1 7. Yeah, that's fine. I think right here I made a mistake in that. Because when I called this should be 2 times y. Well, what is y? Y is not that. Y is A1 8. 2 times A1 and 8. And then that would result in 2 times, so. Well, what is A1 of 8? Put in a 1 and an 8. That results in A0 and A1 and 7. Yeah, like that. It's kind of expanding, but it's a little different. And then this results in 2 times, so you plug in A0 and 0 on the X, A1 of 7 on the Y. So the 0 makes it a 2 times Y. Well, what is the Y? It's A1 of 7. Okay. And then, well, after that you go, okay. So you'd say, well, what is 2 times A1 of 7? Well, what is A1 of 7? So you'd plug in, doesn't go anywhere, so it'd be A1 minus 1, 0 of, and then Y would be A1 and 6. Okay. So you would do that. So what is A0? 0 on the X, A1 of 6 on the Y. So 0 on the X means the 2 times Y. Well, what is the Y? It's A1 6. Okay. That'd be, what's A1 6? Well, the 1 doesn't go anywhere, the 6 doesn't go anywhere, so it would call A 1 minus 1, 0, and then on the Y, it'd be A 1 and 6 minus 1, 5. So it's expanding still quite a bit. So let's keep going. So A0, so plug in 0 and 1 of 5. So 0 goes, and it fits in somewhere. So it's 2 times Y. What is Y? Well, Y is A1 of 5. Okay, cool. Two times, what's A1 5? So plug in, doesn't go anywhere, so it'd be, so that would give you A 1 minus 1 is 0, and then on the Y is an A 1 and Y minus 1, so 5 minus 1 is 4. Okay, and then you keep going. So you keep going, and then so what is, so then you call A 2 times A 0 on the X, A of 14 on the Y. So if you have a 0 on the X, that checks out, so it'd be 2 times Y. What is the Y? A 14. Awesome. I don't really know the parentheses, but this is pseudocode, I don't give a shit. So 2 times A14, so you plug in the 1 and the 4 doesn't fit anywhere, so you'd call A again recursively. What's 1 minus 1 is 0. And then on the Y you call A, and then you call it with 1, and which is the X, and then Y minus 1, 4 minus 1 is 3. So then you do it again. Okay, A0, so you plug in 0 for the X, A13 on the Y, so 0 for the X is a 2 times Y. Well, what is Y? Y is A13. So it's expanding still, it's expanding. So then you do so 2 times A13, well, what is A13? So A13 doesn't fit anywhere, so you call A again. 1 minus 1 is 0. And then you call A for the Y using X, passing in X and Y minus 1, so 2. Call this again. Well, what is A0 on the X, A12 on the Y? Well, 0 on the X, you pass it in, so that works as one of the conditionals, so it's 2 times Y. Well, what is 2 times Y? It'd be 2 times A12. Okay. So what is 2 times A12? So you pass in 1 on the X, 2 on the Y. Doesn't fit anywhere, so you call A again. So it'd be A1 minus 1 is 0. And then on the Y, it would be A, it'd be 1, and then be 1, and 2 minus 1 is 1. Okay. So it's still increasing downwards, which is pretty fucking crazy. So it's increasing downward, and then what do? Well, you go, okay, well, let's keep going. So what is 2 times A0? Well, if you plug in 0 on the X, A11 on the Y, so 0 on the X, so you have a 2 times Y, which is Y is A11. Okay, cool. So you do so what is 2 times A11? So if you pass in 1 and 1, so 1 on the X, 1 on the Y. Well, 1 on the X doesn't really matter, but 1 on the Y does, so that returns 2. So that finally equals 2 times 2 times 2 would be equal 2 times 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 2, which would equal, let's do the calculation. So let's just do it manually. 2 times 2 times 2 times 2 times 2. So that's 5. 1, 2, 3, 4, 5 times 2. So 1, 2, 3, 4, 5. Let me actually just count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's do to the 11th. So 2048. But that's not accurate. Is it 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It wouldn't be times 2 times 2, it'd be times 4. It'd be 4 times 2 times, yeah, I gotta think of it like that. This would be 4 times 2 times 2 times 2 times 2 times 2 times 2. 4 times 2 times 2 times 2 times 2. 4 times 2 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 times 2. So that's 8. So 8 twos. So 1, 2, 3, 4, 5, 6, 7, 8. I guess you could do that. You could do 4 times 2 to the 8th. It's 1024. 1024. Fucking crazy, man. Dude, like, what is this? So how many referred... What is it called? It's called referred operations. Let's see, it's 1, 2, 3, 4, 5. What a shit ton, because you have all these. It's a ton of referred operations. I don't even know, honestly. I don't even want to count that. It could be like 80 or 60 or something. Wow. Actually just ridiculous. That is so cool though. So yeah, it is 1024. God, I'm gonna do all the exercises, so I gotta do it for all of them. Shit. Okay. So I have exercise 1.10. I'm gonna put the pseudocode thing in the adventure thing. Yeah, I think it'd be kind of cool. I got that. Now let's do it for 2 and 4, 3 and 3. So, shit. Okay. 2 and 4. So I'm gonna call 2 and 4, 2 on the X, 4 on the Y. So we call the function again, this time with X minus 1. So 1, yeah. And then we'd call, for the y, we'd call the function recursively, so we'd call 2 and then y minus 1, which would be 3. Okay, and then we call the function with 1, and then it doesn't really matter, so we'd call it again actually. Call it so that means if we call the function a1, a2, I think we wouldn't stack the a's, it would just be, call it again. So we'd call it, and then for the x it'd be x minus 1, which would be, wait, so we'd call it, result in recursion, so it'd be 0 for the x, and then for the y we call a again. But for the x, for the x we use 1, and for the y we use y minus 1, so we'd use, damn, how do you even do that? We'd use I guess a minus. Use an a, 2 and 3, and then minus a 1. Okay, you do it like that. So I think you'd wait for these processes for now. Yeah, I think you would. You'd defer them for now. So you do the a, 2, and the 3. If you passed in the 2 and the 3, it would be, let's see, 2 and 3 would be, so a, 2, 3. You have to pass in a again. Pass in a again. This would result in, so x minus 1, so it'd be 1, and then a to the x, and the y would have, you'd call a again. X would be 2, and then y would be 2. And then you call 1. Like that. So then you'd call a, keep that for now. We'd want to defer it. So defer this. We just want to answer, so the a, the 2, and the 2, what would that be? So the 2 and the 2, you pass in 2 and the x2 and the y, it doesn't really matter. You'd have to call it again. And by calling that again, call a, x minus 1 would be 1, and then for the y you'd have to call a again, and you pass in the 2, and then y minus 1 would be a 1. Well, this is important, so you go, yeah, that works. Well, no then, just be like that. For a, 2, and 4. So then you'd call, okay, a0, a1. So let's go deeper. So then you do that a21. What is that a21? So, well, it does have a y has a 1, so can just return it a 2, which is nice. So then you return a 1. Nice. And then you go A0, A1, negative, so A1, A1, 2. A1. What is A12? Well, it doesn't fit in any of those boxes, so you call it A, and then 1 minus 1 is 0. And then for the Y, it's A, 1, and then 2 minus 1 is 1. Minus 1. Interesting. Interesting. So then you go A0, A1, minus A1, A0. Then you say, okay, what's A11? Well, it'd be 2. So 2. Yeah. Okay, keep going. Shit. Okay. So, okay. So something minus 1, so it'd be A1. Okay, so it'd be A1. You pass in that. Damn, did I do it wrong? Might have done it wrong. I don't think so. Yeah, I don't think so. So A02, so it's 0 on the X, so that would result in 2 times Y, which is 2. So 2 times 2. Basically 4. That. So what's A14? Doesn't fall into any of those categories. Call A again, and then you call it as a 0, and then the Y would be A1, and then 3. Minus 1. A1, negative, A0, well, it's A13, so this one. Well, it's A13 is doesn't fall in any of those. It'd be A0, and then A1, 2. That 1 minus A0, A0. What's A12? There's nothing as well, so it'd be A. Call A again, so A 0, and the AX, so 1 and then 1. Okay. A0, A1, negative, A0, A0, A0. What's A11? Well, it's a 1, so it'd be a 2. A0, A1, A0, A0. So what's A02? So it'd be, oh shit. Okay, so it'd be 2 times Y, which would be 2, so it'd be 4. So 0, 4. I see the light at the end of the tunnel. So A1. No, I don't do that one yet. So minus. Shit. Okay, A04. That means you do. Damn. So you do a 2 times a 4, so it'd be an 8. A1 is minus, so A0, so it'd be 2 times 16, which would be 2 times 16 is or 2 times 8 is 16. So this would be A0, A1. 16 minus 1 is 15. So then this would equal, let's see, A0. So we gotta figure that one out first. So that 1, 15, so it'd be A 1 and then 15. So A0 and then A1 and then 14. So it'd be A0, A0. And then A114, shit. Damn, I feel like that's gonna expand like crazy. Cause that'd be A0, A113. It's gonna be A0, 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 A113 would be A0, A112. Holy crap. It's gonna expand so much. Jesus Christ. There's no way. Am I really doing that right? A111. Jesus. It's not for the faint of heart at all. So yeah, it turned into A0, A110. So it's expanding out again. Holy fuck. God damn. So this turns into A0, 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 A0. What's A110? Well, it calls it and it goes 1 minus 1. A0, A1, 9. This turns into A0, 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 A0. A19 is A0, A. Shit. Okay, A18. A0, A0, A0. A18 would be A0, A17. God damn, and it expands again. It's a huge chain of referred value, or referred processes, operations, deferred operations. So then keep going. A18 is A0, A16. A14, so it builds back up to that. So 2 times 2 is a 4. If you don't know what I'm doing this exercise in this book called Structure and Interpretation of Computer Programs. This book is fucking insane. It is super hard for someone like me, but I'm gonna do it all. This is the pseudocode for me to understand this recursive Ackermann's algorithm or whatever you call it for this one example. And this is a sub example. So 64, so A is a 2 is a 0, so it's 2 times 64 is 128. What is it? 6 divided by 2 times 2 is 512, so 512. Uh, 512. 1024, 1024. I thought this would be easier than the one up here. It's harder. I thought 1 and 10 bigger number, but 2 and 4 has been a monster of a problem. It's crazy. What is that? 2048. Four zero 4096 zero 8192, so 8192 times 2 16 384 384. Ah. $32,768. 65, 5, 3, 6. Wow. I honestly can't believe how fucking crazy this is. Look at that shape. It goes out distinctly and then it comes back in. That's definitely recursive. What a fucking monster. So what is that? 2 and 4. Please be 65,536. Thank God. Oh my God, I got that right. Jesus Christ. It's so hard. It's so hard. I honestly can't believe how hard it is. I'm gonna have to take a breather after this. So I have parts A and B. I'm gonna do part C after this. So, what is it? I will be back. Okay, I'm back. So let's do this. So we did part A and B of exercise 1.10. So this is A, this is B. So I'm gonna do part C, which is inputting 3 and 3. We'll see what the behavior of that is in this algorithm. Let's see, is this cold enough? I'll get a Pepsi pretty soon, but for now I'll just drink some more water. Hope for the best. So, yeah, this book is kind of crazy. But I like it a lot. Fucking love it. I'm on page like 36 and I'm scared because this book is, I think, like 700 pages, 800 pages long. So, I'm in for something that is truly gonna be unheard of for me. But it's gonna be a good time. Because what better do I gotta do than on Christmas break than teach myself scheme and dive into this book, you know? This is the time to do it. Okay. Ready. So, let's do this. Position is better. Okay. So A33. So for this one, okay, I gotta get my mind ready to be able to do these things. So it's gonna go in. Does for a 3 on the X, 3 on the Y. Is Y 0? No, it's not. Is X 0? No, it's not. Is Y 1? No, it's not. So it's gonna call the function again, recursively. X minus 1, so it's going to be a 2, and then the y is going to be calling the function, and then it's going to pass in the 3, and then it's going to pass in y minus 1, so that's 2. So moving on. So A2. So let's figure out what A32 is. It's going to pass in a 3 and a 2. It doesn't match any of those instances, so you're going to call the function again. 3 minus 1 is 2, and then for the y value, so it's going to be 2, and then for the y value, it's going to be a 3, and then 1. This is going to be A2, A2. What is A31 going to be? Well, the y is now actually 1, so it's going to work out quite good for us. So it's going to return a value of 2. So A22 would be, what's A22? So it's going to pass in 2 and 2. Doesn't match any of those. So A2, so it's going to be A1, and then A2, 2, 1. So that's fine. And it's going to pass in, so let's see, what's A1? So A21 has a value of y on it, so it's going to have a 2. It's going to return a 2, which is really nice for us. A2, A1, 2, so that's not going to do anything for us. So it's going to be A, 0, and then it's going to be A, 1, and then 1. So this is going to give us A2, A0, and then A1, 1. Well, it's a 1 on the Y, so it's going to return 2. So it's going to be A2, A. Okay, what's A0, 2? So 0 on the X, so it'd be 2 times Y. So 2 times Y is 4. Oh my god. And now it's going to bring us to an A24. So now that it brings us to an A24, that's what we did the previous one. So we know that A24 is equal to 65,536. So this should equal the same thing because it just goes back to that. I am not going to do that whole thing. I could, but I won't. No. I'll just use our knowledge of that. So what is this? A33? So A33 will actually have the same thing. They'll go the same thing. 65,536, yeah. It's the same thing. Nice. So we're done with that. Let's check it online just because it's 1.10. So oh shoot, there's more to it. I can't look at that. So I know it. I'm not looking. So it'll be 1024, and these are equal. Okay, good. So there's more to it. There's a part 4 to this. Okay, I didn't see what it was. Thank God. So we know all this now. Now we got to consider the following procedures where A is the procedure defined above. So give concise mathematical definitions for the functions computed by the procedures f, g, and h for positive integer values of n. For example, kn computes 5n squared. Okay, so let's give these. So first let's define it on our own. So we have a function f which takes in an n, and we immediately call a function, we pass in 0 and n. And then we have another function g which takes in an n. On each n, pass in an a to an n. And then we have kn. So what this is going to do is if you pass in a 0 and an n in this case, so what does it seem to do? It seems to take So I know that. Okay. So for function f, function g, function h. So for function k, we are doing 5 times n squared. That's what we're doing. For function f, we're plugging in 0 and n. So I'll say this computes 5n squared. For f, this computes what is it? It's called like an Ackermann's. They call it the insane Ackermann function. Well, that makes a lot of sense because I felt insane doing this. It's freaking crazy. Looks like a calculus coder.
And the Ackermann function is defined as a 0, n is equal to n plus 1, right? When m is equal to 0, Ackermann m, 0 is equal to m minus 1, or Ackermann, sorry, m minus 1, 1, when n is equal to 0, right? Otherwise, if these aren't true, then we use Ackermann m, n is equal
This guy plays plutonium.
Ackermann m minus 1, a, so Ackermann m, n minus 1. So this is else, or otherwise. So, to solve a problem when it comes to like the Ackermann function, let's say we're given, solve for Ackermann 1, 0, right? Remember, one is m, and 0 is n. So it goes like that, right? To solve for this, well, we see that n is equal to 0, so we use this equation right here, right? We use this one. So plugging it in, we do Ackermann m minus 1, so m is 1 in this case right here. 1 minus 1 is 0, comma 1. Right. Now, you can see that we can still go deeper and apply another Ackermann function to it. M is 0, so we could use this equation right here. So in this case, we just do n plus, for example, for a good example, could be solve for Ackermann 1 comma 1, right? So neither m or n is 0, so we could use this equation right here. So plugging in, we get Ackermann m minus 1, m is 1, 1 minus 1 is 0, comma Ackermann m is 1, n minus 1, n is also 1, so 1 minus 1 is 0, so comma 0, right? And as you can see, right, we have a nested Ackermann function within a bigger one. So in that case, we always work from the inside out. So work from this inner Ackermann function right here, and we apply a formula to it. So this is m, this is n. So n is equal to 0, we can use this function. Now we're gonna get, let's rewrite it over here, Ackermann 0, comma, and solving for this right here, using this formula, we get m minus 1, right? 1 minus 1 is 0, so we get Ackermann 1 minus 1 is 0.
Wait, so we want to see what it does. So, okay, so yeah, so what this does is it uses the function and it passes in a, what does it pass in? 0 and an n. Which then goes, it goes into, what would it do? Why no would call that a procedure, Ackermann's procedure, plug in that 0 on the x, plug in that n, but because x is 0 straight out, it'd be 2 times n, so that'd end up being 2n. Computes 2n. This one, so we kind of got to follow the logic here. So a one n. So what does this do? A1n, it will take in the 1 for the, okay, nice. So the x, okay, so that doesn't really matter. So at that point, what it'll do for us, so let me think this out. So a1n, so what that'll do is it'll have 1 on the x and on the y. We don't really know whether that works, so that would end up doing a, one it'd be 0, and then a 1, and then n n minus 1. And in this case, it would end up being something like, so a1, well, that wouldn't work, so you take a, b0, a, 1, n, n minus 1. It'd keep going till the nth, so let me see what that would do. Because let's see, like, if that was, let's do an example, like if that was a 3. I'll be right back real quick. Okay, so what was I gonna do? I was gonna test it with, yeah, A13. So yeah, so if I test it with an A1, I did that on the first one, and what did that end up doing? Well, that, for that example, A110, that ended up doing what's up here, so it ended up getting it to 10 to 4. So how many of those happened? So looks like it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 twos. It ended up being 10 twos. So it'd be, this would end up being, this would end up computing to n. Yeah, because if you took that's 1, 2, 4. Yeah. Let's try it again. So what was that? G fucking, yeah, cause if we take in that 10, it'd be 1, 2, 2, 4, and then if we took in, like, let's say 20, maybe 104, blah 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 blah. So it'd be 2 to the 20 power. It's 1,048,576. Yeah. So what's that doing? It's just taking 2 to the n power. That's what that does. Nice. And then this one. So with the 2, what is this? 2n. So do we have an instance where I use 2? Yeah, we do. Right here. So what this ended up doing is, what did I have in it? I had a 4. So if I had a 4 in it, God, I'm not sure how I'd really predict that behavior. Somehow this took this to this. Maybe I could count these. Let's see this square root. So if I had, sorry guys, I'm trying to think about this mathematically. It's kind of pushing my intuition, I guess you could say. So if you had 65536 is the answer, and in that function we put in 2 and a 4, what does this 2 do distinctly? So that 4 must mean something. I feel like it's probably scaling it a certain way. So maybe if I give it a, let's just try the obvious stuff. Let's give it like a square root or something. So 6, 5, 5, 3, 6, square root it. It's 256. What gets to 256? 4 times something to the 4. Is 2 to the 4 256? Can't be. I feel like I'm close. I'm on something. So 655 36 divided by 256. Oh, it is 256. Oh yeah, but 256 squared is 65536. So that would make sense with the 2. You square it. Maybe you square root the 4. Maybe it's like because it'd have to be relating with n somehow. So you'd have like an n. Somehow it's got to equal 65536. You plug in that number. You plug in what we have for n, so you have 4 for n. The 2 is some kind of modifier, so well, if you look at this is just multiplying 2's, a bunch of 2's. So at its peak, it's got to be multiplying 15 of those. But where do we get that 15? No, it's not even 15. Yeah, it is 15, so wait, so it's 2 to the 15 equal to 32,768. So it's 16. Think of it as 16. That gets us our answer. So 2 to the 16. 2 to the 16 is equal to 65536. So how can we relate that specifically with the 2? Oh, yeah, so it'd be 2 to the, yeah, because 2 to the 4, 2 to the 4 is 16. So it'd be 2 to the, 2 to the 2 to the n. That is it. Yeah. Yeah. It computes 2 to the 2 to the n. Boom. That should be it. Okay, let's see if I got it right. Computes 2 to the n. Computes n2. What? Titration? Oh shit, it's right here. Domain coloring a holomorphic tetration. What am I looking at? A gamma abscess 3D PNG. Created with Mathematica language. Okay. Wait. I don't know what that means. But I feel like mine is correct too. Wait, let me ask GPT, because... Wait, is... the same as 2 to the 2 to the n 2 to the n. No, I'm not saying n squared. No, not n squared. I mean 2 with n exponent. I think that's how you explain it to the AI. I got it. You're asking if... No, I mean... what am I saying? Is he saying the n in front of the 2? No, I'm saying n exponent in front of 2. I think it's called tetration, how they say it is. How are they not the same though? Because if you look at this, let's go calculate this. So I'm confused here. Let's take in this h. So h 2 to the, say 2 to the 10. So this would, I think it's going to be 2 to the 2 times 10. That'll be the answer. Okay, it doesn't give any answer. Maybe I wrote it wrong. Either that or just a super big number. Okay. Yeah, I figured it's too big for this, for the sake of this. Holy shit. What have I done? Chat, what have I done? I feel like I'm in deep. I don't know what this number is. I think I'm wrong. Yeah. No, I'm not wrong. This just goes really big. Unless I'm not thinking of it correct. Because... yeah, I am not thinking of this correct. It doesn't do what I think it's going to do. But what did I do before? I did it to the n. Oh yeah. I did a 2 to the 4, which gives this. Why is it that when I go to 5, it becomes a monster problem? I think it grows like insanely big. What about 2 to the 2? Should be really small. Because this is the same as going 2. This is the same as going. Yeah. So there's a key difference I'm not seeing. So this is straight up, this is tetration. I do not know about tetration, but I'm kind of glad I know what it is now. Computes tetration. So I got it wrong. I don't know why I got that. Because I really thought it does work in that case. But if you put it in the case... How I think it is, it would be 2 to the... 2 to the 2 to the 5, which would be this. I think it would be this. But if I do the actual calculation here with a 5 and with a 5, the actual function, it's this. So it's growing like insanely fast. I ran out of memory when I put 10. Yeah, so it's just growing like a monster. So it's not 2 to the 2 to the n, it's tetration. So instead it's, you gotta think of it like, yeah, I just haven't gotten to that yet. I really don't know what the hell that is. So I'm wrong here. It computes into the 2. Tetration. I don't know what that is. Let's look that up. Honestly, like I'm intrigued. It just happened to line up with my thing, but doesn't necessarily make it true. So tetration. So in mathematics, tetration or hyperfour is an operation based on the, not to be confused with titration. For repeated tetration, see pentation. Holy crap. Or repeated exponentiation. Uniterated or repeated exponentiation. There's no standard notation for tetration through Nuff's up arrow notation. Though Nuff's up arrow notation and the left exponent xb are common. Under the definition as repeated exponents, NA means you know what, I think there is a thing that lets you do that. I'm sadly mistaken. Yeah, that shit doesn't exist. Come on. Please be one. Oh, they have like the derivative and all that? That's cool. Okay. Let's not do that. Means a to the a to the a to the a, where n copies of a are iterated via explanation. Oh, I see. So I guess I could think of it like this. I could think of it as two to the n. No. titration. Jesus, man. So, yeah, so if I did, probably not gonna, let's not do that. Let's just do 3. So it'll literally it'd be 2 to the 2 to the 2, 16 to the 2, 256 to the 2, 65 like that to the 2. This is where it, okay. N times. That doesn't seem true though, because 3 times, yeah, it works. 4 times it gives us what, like 2, okay, it gives us that. And then 5 times it goes berserk. Just doesn't make sense to me. That doesn't make sense. Let's try it. To the 2. Is there really titration now? Oh, I see. Yeah, I see. If you had it 4, so if you had it, it'd basically be, we're multiplying by itself. How many ever times do you say? So 1, 2, 3, 4. But you're not doing it like 4 times like that. 1, 2, 3, 4. 2. So that ends up equaling 2 to the 16. Really? So 2 to the 2 to the 2 to the 2. That's only 256. I think 2 to the 16. So I think what you would do is you take 2 to the 2 to the 2. So you have it 16. So then that would turn it to 2 to the 16, like that. So if you had it, let's say with 5, should be 2 to the 2, 2 to the 2, 2 to the 2. So 256 would be 2 to the 256 power. You're getting some monster number. Thing is, I don't think it gives the right number here. E to the 77, yeah, it's a monster. I see. Nah, I like the regular notation for titration.
Hello, and welcome to another.
Gain the unique, powerful capability to search billions of records in less than a second with Cisco Tetration Analytics. You can collect data center network flow information in real time at line rate without any sampling. Comprehensive natural language and visual-based search queries help find details of known issues and other aberrant behaviors that could go otherwise unnoticed. Issues that are critical to an application owner
So I'm done
or
with
to
extras
network and
1.10.
operational engineers.
Wow, that's fucking hard.
Cisco Tetration Analytics Flow
cool.
Explorer provides new ways to analyze data center traffic. It offers you a top-down approach to finding problems with visualization of patterns to highlight details of network and application performance.
Well, if I did it
The
one,
result
it would
is an
always be
intuitive
one.
view of multiple dimensions of data that can be easily narrowed by time, filtered by ranges, and highlighted according to density of measurement. By combining the power of Flow Explorer with the
Threaded
comprehensive
runtimes.
search capabilities of Cisco Tetration Analytics, you can filter
times
views
one
to
times-
see how a
Wouldn't it-
specific
shouldn't it be
application
one?
behaves as a whole, and then see how individual flows compare to other flows in similar categories. The outlier view is especially useful because it shows you flows that differ from others in the Flow Explorer based on a deviation in any of the captured data points. Highlighted anomalies are a quick visual identifier of deviation and eliminate the need
What
for
am I
manual.
looking at? I shouldn't be looking at that. Okay. The nuts up arrow notation. What is that from? Where's GPT? So what is tetration from? Calculus class? I know it's not, guys. Wait, what? Okay, yeah. It's not. It falls into the realm of advanced or specialized math studies. Advanced mathematics? Jesus, dude. It's honestly insane. Oh, wow. Holy crap. What am I looking at? It's kind of mesmerizing. Hue. What is hue? Just kidding. Freaking color theory. Not today. Not today. Okay. Let me save this, and then let me set it up and let me send it to GitHub. Added more stuff. Yes. Commit this to me. Sussmans. So I got my pseudo text here. Nice. This is honestly I love having this file. It's so simple, but it honestly keeps things way more in track. What? Oh. dot racket. Nice. Cool. Let's continue on. I think it's time to crack open the Pepsi. Yeah. I think it's time. And then I'll learn about tree recursion. I'll be back. Real quick. I promise it'll be quick. But honestly, I don't really care. You know what? Actually, I'm gonna call it. I didn't realize I've been going for 4 hours and 37 minutes, so let's call it. Tree recursion. I need to give it justice, so I will pick up on this soon. So until next time.